Right? Bismillahirrahmanirrahim. Hello, everyone. So we are now looking at June 2016 paper 52. Okay. Specifically question number 2. Okay. So what this setup is showing you is that you have a volatile liquid in a hypodermic syringe. Hypodermic syringe means a syringe that that is connected to a needle, just like the syringe that they use for injection. Okay, so this is obviously different to gas syringe, which is something that you are more familiar with, the syringe that you use in the lab, but the bigger version. Okay. Since my connection is unstable, right? So what happens is that you put some amount of the volatile liquid. Volatile means it turns into gas easily. Okay. So it evaporates easily, it turns into gas easily. So you put a certain amount, and then it is connected to a gas syringe, which is the bigger syringe, and this gas syringe is put under a hot condition. Okay, so that steam jacket just means that the gas syringe is surrounded by steam, so that means this region is the hot region. Okay, so obviously the reason why you increase the temperature, you want to make it hot, is because so that the liquid turns into gas. Okay. Now, it is the same. It's the same liquid, it's just the different state. In this hypodermic syringe, this is the cooler region of the setup, there will be a certain volume, a certain mass, we use mass, okay? And then once you inject that liquid, when it goes into the gas syringe, it turns into a gas, okay? Even though they are the same molecule, you have done nothing to them except that you have changed the state from liquid to gas. Now, for molecules in liquid form, the molecules are much closer together, okay? But in gas form, they are further apart. So a 1 gram liquid may take up a bigger amount of space in the gas state. Okay, so liquid may be just like a small section like that, but then when it turns to gas, maybe it takes up, a bigger space. Okay, so that's what's happening. They give you the relationship. The V here is the volume of the gas syringe. Now, for gases, it is not easy to measure the mass because gas will be very, very light. So we take the volume instead. Okay. And then that's some terms. The MR is the MR of the volatile liquid Y that we want to investigate. Okay, M is the mass of Y when it is in the liquid form. Okay, when it's liquid, it's easier to weigh the mass, right? Why don't we use volume? Well, I guess it's easier to weigh the mass because small difference in mass can be detected by the weighing balance. But if we read the reading here, small amount, small volume will be difficult to read, okay, or not accurate. But of course, you can also read the volume, but in this case, we use the mass. Okay, right. So what happens is that they start with 5 centimeter cube of air, okay, which is, just the starting point. What they don't want to start at 0. That is, just you can start with 5 centimeter cube. You can start with 3, 10. Okay, it happens to be 5 in the setup. So you allow the temperature to reach 100 degrees Celsius. So that's a high temperature. Okay. Once the air in the gas has stopped expanding, so that means once the piston stays constant, that is the volume of air. Okay, that's your volume of air already. So what happens is then you inject some, okay, so a little liquid Y is injected into the hot gas syringe. Okay, so you just inject a small amount of liquid so that it goes into the gas phase. Okay, and then after that, after you're done injecting and the gas Y has stopped expanding, then you weigh the syringe and liquid Y. Okay, so you weigh this after injection. right? That's because you want to know the mass before injection and the mass after injection. That means how much have you injected into the gas syringe, okay? For the gas syringe, you don't have to wait. You just read the initial volume here, and then maybe the final volume is somewhere here. And that is the amount of gas Y, okay? Remember, this part is your air molecule. That's why you have to do some subtraction. Okay, so then the maximum volume is recorded. The mass of liquid Y is recorded, calculated and recorded. Okay, so you have this table. Right, I don't have my values here, but your first values should be on the first row, 0.15 and 48, and then the last one should be 0.22 and 73. Okay, if you got the first and the last one correct, then everything hopefully should be correct. Okay, and then they ask you to plot a graph. Use a cross to plot each data point, draw the line of best fit. Okay, so I believe that after you plot your graph, the best fit, line of best fit does not necessarily mean it is always a straight line. Okay, a curve can be a line as well, but for this question, I think yours is nicely a straight line. Okay, and then you have anomaly. Did it say to circle an anomaly? This can cause, okay. So you will choose make sure that you mark your points with an X, okay? Not a dot. They already say use an X. If you use dot, that means you're not following the instruction. So use X, maybe your points look like this, okay? So anomaly is an outlier, basically points that are far away from the expected value, okay? So from my drawing, I don't know how yours look like. I also forgot to check with the other block. This is anomaly because it is far away from the line, okay? It is higher than expected. This one, I'll make it a little bit further. This point is another anomaly, and it is lower than expected, okay? So there are a few reasons why some readings are higher than expected or lower than expected, okay? It depends on the type of experiment. Usually when the point is lower than expected, that means you may have lost some masses unnecessarily, okay? Like in the case of this example, it would be like evaporation. There is evaporation happening, which is not a part of the reaction that you want, a part of the setup that you want. Why is it higher? For this experiment, maybe not so much can be explained when why the mass is higher. But if you're talking about like decomposition or dehydration of a solid, sometimes the mass is higher than expected. This just means that you have not removed all the water completely, or that the reaction hasn't gone finished yet. All the gases that you are supposed to lose have not been lost completely. Okay, so there are a few reasons that you need to think about, and by now you should already you should practice and start to think about logically, because these answers will not be in your notes. Okay, right. Again, you may not have this point in your plots. I don't know how your plots look like, but let's just move on. Okay, so liquid Y evaporates easily even at room temperature. So Y is a volatile liquid, right? So even if it's not at 100 degrees, even if you have not pushed the liquid into this hot box, okay, I will call it a hot box, the liquid is already naturally evaporating. You cannot help it, okay? So this can cause anomalous results, giving points below the lines of best fit. Okay, so this tells you that the mass of the Y is decreasing, but the volume, like here, okay, so the mass of Y is decreasing, but then it escapes as gas to the atmosphere, not into the gas syringe. Okay, so this is one of the reasons why your value can be lower than expected. Okay, so explain how such anomalies occur when you have points lower than expected. One of the, well, there are three reasons, okay, that they give. The first one is that Y evaporates from the syringe, okay? Even before you inject the syringe into the hot box, the Y naturally evaporates because it's volatile, right? Okay, so Y evaporates from the syringe. Okay, and then I'll talk about the second one. There are 3 points, but I'll talk about question 1 and question 2 because they are related to each other. With reference to the experiment procedure, explain how the source of error could be minimized. So solution, okay, if Y evaporates from the syringe even before injection, naturally because it is a volatile liquid, what can you do to solve this? Okay, so one solution is to make sure that the hypodermic syringe to be as cool as possible. Okay, why? Because temperature also affects the rate of evaporation. Okay, so if you make this syringe really cold, then it will stay as liquid. It will not evaporate. Maybe at room temperature it evaporates. Then put this in an ice, okay? Or surround this volatile liquid with ice. At least you know that the liquid will stay as liquid. It will not evaporate unexpectedly, okay? Because the idea is we do not want the liquid to evaporate. We want them to go into the gas syringe where the hot box is, okay? So that's one error with the solution. Okay, the second possible error, I'm going to use a different color, is well, it's more or less the same. Y evaporates before injection. Okay, before you start the reaction, Y is already naturally evaporating, as I said, because it is a volatile liquid. So how do you minimize this error? Before you start the reaction, you cover the end of the needle. The end of the needle. Okay, because the, yes, Isa, I think your mic is on. Okay, so you cover the end of the needle, where, you know, where the liquid is coming out. Cover it and only open it when you are starting the reaction or starting the injection. Okay, and then the last one is Y could also evaporate. The liquid also can evaporate before weighing. Okay, well, they all sound the same. Okay, it's all about evaporation, but it's just different time of evaporation. Okay, so remember, after injection, you need to weigh the hypodermic syringe. Okay, like after you inject some liquid into the hot box, you will have to remove this setup and then you take it to the mass balance. So obviously, inevitably, again, because you are doing that, you are weighing, you're transferring, there will be some amount of time that have elapsed. Okay, so there will be some evaporation happening. Okay, so how do you solve or minimize that problem? It sounds a bit funny, but you could, you could minimize the length of time between each weighing. Okay, so that means you do not, you know, take a walk in the park and then you waste your time and take your sweet time weighing the hypodermic syringe. Okay, so you want to take it off the setup, wait, and then quickly return it back. Okay, so the longer time you take, if you put the syringe on the table and you wait, you queue some more, then obviously a lot of evaporation would have occurred and you will lose a lot of mass of Y. Okay, right, next is to determine your gradient. Can you please do this? It's a straight line, so you can just choose any 2 points that is easy to read. Okay, please do not choose like points that are, I don't know, maybe 3.725 or something. Okay, choose a nice and easy points to read. Write down the coordinates and then you find the gradient. Okay, can you do that? And then let me know when you're done. If you've done this earlier already, we'll just wait for the others. Okay, is everyone okay? Unmute all participants are unmuted. Do you have your calculator with you?
Yes.
Okay, I hope you do. I forgot to remind you to bring your calculator with you. Perhaps you can use the calculator on your phone or on your laptop, that's fine.
And the cross banner.
What do you mean, Ang left my calculator at home? You are home. Where else would you be? Ang, how come I never hear your voice? My screen sharing is paused. Okay. So I need your values. Can I have, if you already found the gradient, can we know the sort of values you are getting? If anyone have found their gradient. Ban has got 350. Anyone else?
I got 333.
333, 357. Resume share. Oh, it was recording. I meant to pause the recording and not the sharing. Okay, can you see my screen? Okay, it's moving. 357, 350. Some may be a bit higher, some may be a bit lower. It all depends on how you draw your best line of best fit, and that is fine. Okay. Fortunately, you will not be penalized if you get like yeah. So most of you are in the 350s. Eric 350 anymore? Kai Xiang? Kai Xiang 350 as well. Okay. Who else is there? Nick, Iqbal. Have you guys calculated? Is Mukri here? Yes, Mukri is here. Okay. Right, Mukri might not have plotted his graph because I did not, because he was not in school. Right. So I'm guessing that most of you got around 350. So I'm going to use that value, 350 gradient. Okay, the next part is use the gradient and the mathematical relationship on page 7. So we go back to page 7 and you've got this mathematical relationship. And because you got a straight line, so you would imagine that you have a ymx plus ymx plus c. Okay, so your gradient m is this part, this expression. Your y-axis is the volume. Okay, how do you know that? You check your y-axis, volume. Your x-axis is the mass. Okay, plus C is 0. That means your line has to pass through the origin. The y-intercept is 0. Okay, so from here then you can know like how your graph should look like. Okay, this is a y mx plus c expression, therefore it must be a straight line. Okay, right. So what do? You use whatever your value of gradient is, and then you equate it to 3.07 times 10 to the power of 4 over the MR. Okay, so we all have different values of gradient. So you sub in the gradient, your number of the answer from your gradient here, and then you work out the MR. Okay, so let me know what sort of MR you are getting. And of course, your MR cannot be like a funny number like 0.0 something something. Okay, 87.7. Okay, that sounds good. That sounds okay. Any more? Okay, 87.7, because most of you got the same gradient, which is 350. But for those of you who did not get 350, you should have more or less, you know, similar MR. $87.9. 86. Okay, that's fine as well. 87.7.
What?
Okay, so if you get an answer that ranges from 80 to 90, I'm guessing that is a good sign. Okay, but if you get an answer that is like really off, like 0.00 something, then you should be worried. Okay, if your gradient is in the regions of 350s, then should be your MR is should be around that window as well. Okay, so compound Y is a hydrocarbon. That means it contains carbon, it contains hydrogen. Okay, and it contains 85.7 carbon by mass. So Y contains carbon and hydrogen. 85.7% is carbon. So that makes your hydrogen how much? How many percent? I have a calculator in front of me, but I don't want to do the calculation because I know you can do it for me. Percentage of hydrogen if carbon is 85.7% by mass. 14.3, thank you, Inshira. 14.3%, okay? So you know the percentage mass. When they give you the percentage mass or the mass, mass composition, you can find the empirical formula from here, okay? Even though the question is not telling you to find the empirical formula. So that's up to you to be smart to spot that finding the empirical formula can help you find the molecular formula, okay? Because molecular formula and empirical formula is related. So I hope you still remember how to find empirical formula. Given the percentage mass, what do you do next? You divide by the AR, okay? Carbon is 12, hydrogen is 1. So you will get some, so why do we divide by the AR? Now you see here, this one is, I know it's percentage mass, but you can see it as mass. Mass divided by AR is number of moles, mass over AR or mass over MR, number of moles, okay? So you want to find the mole ratio between carbon and hydrogen. What is the mole between these two? What is the ratio between carbon and hydrogen? Okay, so can someone give me the ratio? Ayo, I want the number lah. But yes, CH2 is right, but the number. Not 1 to 2. Number. 85.7 divided by 12. 7 point, what's the other one? 14.3. 7.14, 71 pulang. Thank you. 7.14 to 14.3, and then you divide by the smaller number. Okay, why do you want to divide this by the smaller number? Basically because you want to get a ratio of 1 out of something. Okay, and it turns out it's 1 out of 2. Okay, so it's CH2. Now this is only the empirical formula. You want to find the molecular formula. The molecular formula is the complete formula, the exact number of carbon and the exact number of hydrogen in the formula. So this brings you to the mass spectrum. Okay, the mass spectrum is mass spectrometry, something that you have learned already in AS. Okay, so these are all the fragrance, right? The hydrocarbon goes into a mass spectrometer and then they are broken down into fragrance. So on the relative abundance, it's just telling you how much of that fragrance is present. But the more important thing is the mass to charge ratio. Okay, it tells you the mass of the fragrance. Okay, fragrance means the pieces. Okay, not fragrance as in perfume. Okay, so if you look at the x-axis, all right, so the biggest mass here is this one. The biggest as in the highest mass, not the highest peak. Okay, I'm not interested in the highest peak. I'm only interested in the highest mass, which is somewhere there. And it turns out that that value is 84. So this tells me that compound Y has an MR of 84. Okay, empirical formula is CH2, but the MR of Y is 84. So you need to find a molecular formula using this relationship. Molecular formula is equals to N times empirical formula. Okay, so if your empirical formula is CH2, how many times of N? How many times of N? How many times of CH2 makes up a molecular formula that will give you 84? So this would be, you can either do a trial and error or the second one later I will show you. 6 times, okay, 6 times of your CH2. So that means it's C6H12, okay? Another way of doing this is, you know the MR is 84 of the unknown formula, and then you know that your empirical formula is CH2. So you take your 84 divided by the MR of your CH2, which is 12 plus 2, 14. Okay, this is the MR of CH2. So if you take 84 divided by 14, you will get 6. Okay, so 6 times, you have to times 6 carbon and 6 times 2 hydrogen. The ratio is always 1:2. So if there are 6 carbon, the hydrogen will be 12. Okay, right, so that is all for today. Tomorrow I will give you a new set of paper 5, right? Any questions before we go?